Last week we started our discussion of enzyme mechanism by considering the simple kinetics of an enzyme-catalyzed reaction. This week we're going to extend that discussion by first talking about how an enzyme and a substrate bind and how that binding can facilitate enzyme catalysis. There are a few key concepts that I want you to be aware of. First, that we have weak non-covalent interactions between the substrate and the enzyme, and that as the catalysis proceeds, the complex proceeds through a transition state. We're familiar with that idea. And that, most importantly, the transition state complex is more tightly bound to the substrate than is the more weakly bound preliminary complex that forms. So, by stabilizing the transition state, enzymes lower the activation energy of the reaction. Last week we introduced this mechanism in the context of Michaelis-Menten kinetics, and we considered how an enzyme binds to a substrate to form an ES complex, known as the Michaelis complex, and how that complex then reacts to form products. This week we're going to expand on that mechanism a little bit and explore the nature of the ES complex, as well as to look at how that differs from this transition state complex, EX double dagger. Let's review transition state theory. We're all familiar with the picture of an uncatalyzed reaction. We have some substrate, shown here, at some free energy, represented by the position on the y-axis. And as the reaction proceeds, the energy increases through a transition state and then lowers again as products are formed. This difference between the energy of the reaction reactants and products, or the substrate and products, is the free energy change of the reaction, delta G, a thermodynamic property. This quantity here, though, delta G double dagger, is the activation energy. The energy that the complex, that the substrate has to achieve to actually form the products. And it's this energy difference that determines the rate of the reaction. The larger the activation energy, the slower the rate. Okay, so when we consider catalysis, the important quantity to be minimized is this quantity here, the activation energy. And how can we minimize that delta G double dagger? Well, we need to make the gap between the ES complex and the EX double dagger, or the transition state complex, as small as possible. So how is that done? Well, it's done by making the ES complex as close in energy as we can to the unbound enzyme and substrate complex, and to make the EX complex, or the transition state complex, as stable as possible. The enzyme lowers the activation energy by binding to and organizing the reactive groups so they're close to one another. So if we consider a bimolecular reaction where two reactants are going to come together to form products, in the uncatalyzed reaction, the two reactions the two reactants are just free in solution. They can go wherever they want to go. And when they react, they have to come together in a fairly constrained and rigid orientation with respect to one another. And this is an unfavorable reaction or situation with respect to entropy. Not only that, but the enzyme provides catalytic groups that we'll see in the next lecture assist in the bond breaking or making and stabilization of the transition state. Let's talk about formation of this ES complex. Last week we emphasized binding, which occurs when the enzyme and the substrate come together to form the bound complex in the active site of the enzyme. And we might think that this binding, being favorable, occurs with some delta G of binding, and the favorability of this has to do with the fact that we're going to be forming those non-covalent forces that we discussed earlier on in the course. In other words, we're going to get this lowering of energy through hydrogen bonding, electrostatic interactions, the hydrophobic effect, and van der Waals, etc. So you might consider a picture where we have this ES complex that's far more stable than the enzyme and the substrate alone. But if we have this pretty sizable stabilization, it is not going to favor catalysis, because what we're really interested in is the gap between the enzyme substrate complex and the transition state. And we see that by lowering the energy of the ES complex, we're making that gap relatively large. What we want to do instead, so this is really not a good way to think about the enzyme substrate complex. What we want to do instead is lower the energy just a little bit. And we're going to be lowering that energy through, again, formation of those non-covalent forces. But we're not going to make them too strong. We're going to make them big enough so that the enzyme substrate come together, but we're going to make them such that they're somewhat strained and distorted, and that the substrate's not too comfortable, not as comfortable as it was in solution. In solution, it's going to be solvated by water, but removing that water is going to destabilize the substrate to some degree. And we are definitely not favoring the formation of the ES complex through entropy, since the ES complex is more constrained in its mobility than the enzyme and the substrate are alone. By making sure that the ES complex is not too stable, we favor catalysis by making this gap smaller, the gap between the ES complex and the transition state. In the last slide, we discussed how we don't want to have the energy of the enzyme substrate complex stabilized too much, because then we would have a really large activation energy. So the better representation of that stabilization is on this graph on the right-hand side of the page. Now we want to take a look at what we want to do to the energy of the transition state complex, EX, double dagger. Here, we want the enzyme to stabilize that maximally. In other words, to reduce its energy as much as possible through binding to the enzyme active site. So by lowering the energy of the EX complex and making the energy of the enzyme substrate complex as large as possible, we make this activation energy as small as possible. enhancing the rate in catalysis. This idea of binding to the transition state best was proposed pretty early on by Linus Pauling, and it's been subsequently confirmed by experimental evidence. We see that the enzyme active sites are really complementary to the transition state of the reaction, not the substrate and enzyme complex, and that these strong interactions lower the activation energy. And the experimental evidence that supports this is through studying the binding of transition state analogs, molecules that don't mimic the substrates, but mimic in their shape the shape of the transition state of the reaction. These bind to enzymes very, very well. All right, so this is really the picture that we want to have in our minds when we think about enzyme catalysis. So what I've just discussed is the presentation that Grisham and Garrett have for this notion of stabilization of the transition state in an enzyme active site. But here's another way to think about the same material. This is a figure from Leninger, another biochemistry book. And here we're considering an enzyme called stickase. It's an enzyme that catalyzes the breaking of some sort of a rod. And in the uncatalyzed reaction, we have this picture where we have our metal stick, and it has to, in order to break, it has to bend in this transition state and come apart. And without anything to help that along, we see that the activation energy, the energy required here, is fairly large. Okay, so this is in the uncatalyzed situation. But we can think about a catalyst that helps this along. And in this catalyst, we have a kind of a magnetic lining here that's going to attract the stick. And if the enzyme has this sort of V shape, we can see that this attraction is greatest in the transition state. So this conformation is stabilized, and we see that stabilization by the magnet as lowering the energy of that transition state by some amount here. We also have a little bit of attraction, but not too much, for the enzyme and the substrate. And we see that in this picture, that really doesn't do very much at all for the stability of our enzyme substrate complex. So this energy is, well, about the same as the substrate in this particular picture. Actually, we're probably better off to lower it a little bit, but very, very little. So by making this as high an energy as we possibly can, the bound complex, and stabilizing the transition state as much as possible, we minimize the activation energy. Okay, so let's just consider B for a second. What would happen if we bound the enzyme and the substrate as strongly as possible? Well, then we would have a situation where the ES complex is super low energy, and there's no tendency for a complex that already is so very stable to achieve this activation energy and catalyze a reaction. So this is just another way of thinking about it. We have a picture where for an enzyme to be an effective catalyst, it needs to bind to the substrate, but not too very well, to really stabilize the transition state to lower its energy and achieve a minimal delta G double dagger.